Hi, everybody, and welcome to our first calculus video. So we're going to begin our discussion of calculus with a really central theme that we're going to build upon throughout the entire course, which is limits. So if you recall from pre-calc, you guys should have seen a little bit of limits towards the end of that course. And limits is a really important concept for really everything that we do in calculus, but it can often get misunderstood or misinterpreted. So a lot of people think of limit as just simply the value of a function at a given value of x. And while sometimes that's true, that's not always the case. So more accurately, when we think of a limit, we want to focus on what the value of y is approaching as x approaches a particular value. So it's not always about what the function is equal to at a given value of x, but rather what it's working towards. So evaluating limits is a way for us to analyze where things are headed rather than just where they are at a certain moment. And for a lot of what we do in calculus, figuring out where things are headed and how a pattern is changing or approaching a particular value is really important to us. So then our formal definition for a limit says that given a function f, the limit of f of x as x approaches c is a real number r if f of x can be made arbitrarily closer to r by moving x sufficiently closer to c. So that is a really fancy way of saying that as x gets really close to a particular value, then y is also going to get really, really close to a particular value, and that value is r, which gives us this notation down here for a formal limit. And so we read this as the limit as x approaches c of f of x equals r, or some real number. So now we have to talk about how limits exist. So there's all kinds of different possibilities when we evaluate limits, but there are a couple of rules that we have to follow in order for that limit to exist. So the first one being y must be approaching a finite number. So what's a finite number? Well, it's any number you can think of as long as it's not increasing or decreasing without bound. So without bound means basically as long as I'm not going to keep getting bigger and bigger forever and head towards positive infinity, or as long as I'm not going to decrease more and more forever and head towards negative infinity, then that satisfies this first condition. Second condition is that y must be approaching the same finite number from both the left and the right side of our indicated value of x. So that means I can't be approaching one finite number on one side of the graph and then another finite number on the other side of the graph, because the two portions of the graph are not going to link up. So we have to be going to the same place in order for this limit to exist. Notationally, we represent those one-sided limits by adding a little direction to the top of the c value that we are approaching. So when you see a negative sign, that means we're approaching it from the negative side of a value. And if you think about a number line, no matter where that value is on the x-axis, negative numbers will always lie to the left of that value. Positive numbers will always lie to the right side. So when you see as x approaches c from the negative sign, we interpret that as from the left. So as we approach x equals c from the left, and as we approach x equals c from the right, as long as those two equal the same value, then the limit as x approaches c is equal to that value. So you can notice here that there's no longer a symbol in the little sub or superscript portion of C. So that means we aren't indicating a direction, so it represents the limit as a whole. So in order for a limit to exist, the function does not have to be defined at the value of x. So that is super important. Again, that's what I was talking about at the beginning of the video as far as misinterpretations or common misconceptions with limits. There does not have to be a point at the value of x on a graph for the limit to exist, which means it is possible for a graph to have a hole or a removable discontinuity at a particular value of x that we are concerned with. So again, if you think about the two conditions, y must be approaching a finite number, and it has to be the same finite number from both the left and the right side of c. So as long as I'm approaching a particular y value, this hole has a finite value for its y coordinate. It's just that value of x is not defined or in the domain of the function. So when we get there, it's a hole. But as long as we're approaching the same y coordinate from both the left and the right side of this value of x, then the limit does exist. So holes are really the biggest problem when we talk about misconceptions or where students typically have confusions when taking limits. So if there's a hole in the graph, as long as there's not a break discontinuity, which we'll dive into a little bit later on, that limit can still exist. And that's what we talk about when we say we don't care about what the function equals, we care about what the function is approaching. Because this function is not equal to anything at x equals c, but it is approaching a finite value, and it's the same finite value from both sides. Therefore, the limit at that value of x does exist. All right, so now we're going to dive into some limit notation practice. So just being able to practice and work with how we read and how we interpret the limit notation. So I'm not going to necessarily write anything down for these, so I'm just going to talk about the notation and help you guys practice saying them. So for the first one, this is read as the limit as x approaches 2 of f of x equals 4. So if we interpret what it tells us about the function, well, the limit exists at x equals 2. So using the definition and going backwards, that means on the graph of f of x at x equals 2, there must be some kind of connected graph from the left and the right side at the coordinates 2, 4. So what we don't know for sure, just based off this limit notation, is whether that point is a hole or a defined point. So the graph could look like this, where there's a hole at the coordinates 2, 4. It could be a solid dot, so a defined point at 2, 4. Or it actually could be something really crazy where there's a hole here, but the point is defined elsewhere, like in a piecewise function. So even in a case like this, where there's a weird extra point defined somewhere else, if you were just looking on a table of values as x gets really close to 2 from the left and right side, those y values are going to keep getting closer to 4. Even though it's defined somewhere else and we jump up to this point, that limit still exists. So there's all kinds of different possibilities when we talk about what this notation translates into as far as the graph goes. But we know that there's some kind of connected graph at the coordinates 2, 4. It's just we're not sure what it's connected to. Is it connected to a defined point or a hole? To answer that, we would need more information than just this limit notation. All right, the second one. This is read as the limit as x approaches infinity of f of x equals 3. Okay, well, when we talk about limits at infinity, so when x is approaching positive or negative infinity, we're really talking about the end behavior. So this is referring to as the graph continues all the way to the left or the right, what are the y values doing? So if you think about most typical functions that you guys have seen before, like polynomials, your arrows are always kind of heading up or down. So like a quadratic function or a cubic, our arrows just kind of go up and down forever. Or even exponential graphs. On this right side, it's going up forever. But an exponential function has a unique characteristic on one side where it flattens out and is actually approaching some y value as we go to either the left or the right. And that is actually what's going on here. So if you imagine a graph and we are approaching positive infinity, which means we are continuing to the right forever, this is saying that the y values are getting closer and closer to 3. So what's going on before that, we really have no idea. There's just based on this limit notation, there's no way of telling what the graph is doing before that. But we do know that as the graph gets closer and closer to infinity, which means we just continue moving to the right, this graph is going to be leveling out. Now, it may be coming down from above and flattening out to 3, or it could be coming from below and moving up and flattening out to 3. But what we do know for sure is that this function has a horizontal asymptote at the equation or at the line of y equals 3. So as x approaches positive or negative infinity, if our limit exists and it's a finite value like that, that's actually telling us that there is a horizontal asymptote on that graph. All right, next one. The limit as x approaches 2 from the negative or the left side of f of x equals infinity. All right, so this is kind of a flip-flop version of the last one. Now we kind of flipped the infinities and the values. So now I'm thinking about x equals 2. Be very careful that you don't accidentally misinterpret this as -2. That's not what this is saying. So we have x equals 2 on our x-axis, and we are indicating that we are starting from the left side and moving towards this value. So now it's kind of like a barrier. We are thinking about as we get closer to this imaginary line on the graph at x equals 2, the y values are heading towards positive infinity. Well, for y's, that means the graph is moving up, and it's moving up without bounds. So that means as we get closer to this imaginary line, this graph is going to be increasing without bound. It's going to continue, the y values are going to continue to get bigger and bigger and bigger. So this is indicating a vertical asymptote. So we have a vertical asymptote on this graph at x equals 2. All right, and now the last one, the limit as x approaches -3 from the positive or right side of f of x equals 8. Okay, so we have -3, so that's the value of x that I care about. We're approaching it from the right side. And now this time we're approaching a fixed or finite value. So at this point, we know that as the graph, it can do whatever you want to on this side. I'm just making something that looks crazy. We know that we are heading to finite coordinates of -3, 8. What we don't know, though, is when we get there, is the point defined or not? We also have no idea about what's going on the left side of -3 because we're not told that information. But all we know for sure is that as we approach -3 from the right side, we are heading towards fixed finite coordinates of -3, 8. So to answer anything more about this graph, we would need to know some more information besides just this limit. All right, so now we're going to flip it around and try to create limit notation for a given description. So for the first one, it says as x approaches 4 from the left, f of x approaches 9. So we're just going to come up with the limit notation. So we need our x value 4. So again, if a direction is indicated when we read or describe the limit, then we have to indicate that with the notation. So again, left is like saying from the side with all the negatives on it. So that would be 4 with a little negative in the superscript of our function f of x equals the limit, so 9. So it is a good bit easier when we are given the description to translate it backwards. So for this one, as x approaches -2, f of x decreases without bound. So notice there's no direction with the -2, so that will just say x approaches -2 of f of x. And then for the equals part, we're not given a finite value like the last one. Now we're saying it decreases without bound. So technically, you could say that there is no limit because we're not approaching a finite number. But when we decrease without bound, that's a specific kind of information, similar to up here. We were told that this limit is approaching infinity. So even though technically that's saying the limit doesn't exist, it's not a case where we don't know something about the graph. So saying it decreases without bound forever just means the y values are approaching negative infinity. If it were positive infinity, then it would be increasing without bound. And then for our last one, as x approaches infinity, f of x approaches 3. So this is actually the same information from the second one up above, where we are approaching that horizontal asymptote. So limit as x approaches infinity of f of x equals 3. So now we're going to talk about how we actually find limits. So there's several different methods for evaluating limits. We're not going to take a look at all of these in this section, but this is what the next few sections will be focusing on. So we can look at the graph of a function. That's usually the easiest way to do it, but that also requires us to actually have a graph or the means to come up with the graph of a function. But we can simply look at where we're heading on the graph, given the directions from the limit notation or maybe a description. If we have a table of values or have the means to create a table of values, then we can continuously make our x values get closer and closer to our indicated value of c and see what's happening to the y values as well. If they're approaching a number from the same number from both sides of our value of c, then we can see that the limit exists and tell what it is. We could try using direct substitution. So this is the most common way that we attempt to make or evaluate limits, and it's exactly what the name says. We plug the value of c into the function to see if it is defined at that x value. If it is, then the y value at the point actually is our limit. So this is the best case scenario. This is where a function is defined at a point at the value of x that we're worried about, and because it's defined and it's meeting up from both sides, the value of the function at x equals c is the limit as x approaches c. If that direct substitution method fails, then we've got a couple other algebraic techniques that we can use to manipulate and rewrite the function and then be able to evaluate. So we're going to take a look at these first two methods. So looking at it with a graph and then a table of values in this section. We're going to save the algebra side for our next discussion. So here we've got a little graph of f of x. You can see some funky stuff going on there. And we're just going to work our way through talking about these limits and pointing out some stuff as we go. So the first one that we want to know the limit as x approaches 1 from the left side. So here's 1. We go up here, we're just going to eyeball this. I might not be exactly at 1, but we're going to play pretend on this one. So as we approach 1 from the left side, now notice I drew in a fixed dot like this guy on the graph. If you are ever working on a graph and there are no points drawn on the curve, then that is because there's an infinite number of these regular, well-defined points packed in really close together. So it is always safe for you to assume that on a smooth curve is a defined point. If there are undefined points like a hole or removable discontinuities on a graph, they must be indicated to you on the graph that's given. So there's no way that I would ever expect you guys to know that there is a removed point at x equals 3 on this graph. That would just be impossible for anybody to know. So it is always safe for you to add defined points onto a curve. So that's what I did right here, just so we have a view of this. So as we approach 1 from the left side, so on the x-axis, I'm moving from the left, but that means on the curve, I'm working my way down towards this point. We are approaching a y value of 1. From the right side of 1, so same thing, I'm working my way up on the curve. We are actually headed to the same point. So because these are the same limit from the left and the right side, that satisfies that second condition. So the limit at x equals 1 overall is defined. The limit does exist, and it is positive 1. For the second row, limit as x approaches 2 from the negative side or the left side. So here's a little something weird that's going on. We have a break in this graph. This would have to be a piecewise function because all these different pieces that exist on this graph. But as I approach 2 from the left side, we are approaching this hole, which has a y-coordinate of 1. But as I approach 2 from the positive side or the right side, we're working on this other piece of the graph, and we're moving up towards a y value of 3. So because these one-sided limits do not meet up, we don't arrive at the same place, this limit at x equals 2 does not exist. So we abbreviate that as DNE. If you want to write the whole thing out, that's fine too. So that fails that second condition. Even though both sides are approaching a finite value, they're not approaching the same finite value. Therefore, the limit does not exist. Fun fact, just to add on to this, if I were to ask you for the value of f of 2, it wouldn't be 1 or 3. Even though from the left side I'm approaching 1 and from the right side I'm approaching 3, this is one of those functions with an extra defined point in there. So when we are asked for the value of the function, now we have to concern ourselves with where is the defined point, if there is one. Sometimes there may not be, but in this case there is. So in this case, the value of the function at x equals 2 would actually be positive 2 because of that extra point that's defined in there. All right, let's try this next graph. So for this one, this looks like a linear function, but there's a hole on the graph. So this would actually be a rational function that has an extra factor in there that we remove out. And I can actually come up with the equation here real quick. So this linear function has a slope of 1, y-intercept of 2, which means I've got a factor of x plus 2 up top. The hole is at x equals 4, which means top and bottom shared a factor of x minus 4. And because of that, they cancel out and remove themselves from the function, which removes that point from this graph. So this original graph, when I typed it into Desmos, was the equation x squared minus 2x minus 8 all over x minus 4, just in case you were wondering what the graph looks like. So to evaluate these limits, we want to know as x approaches positive 4 from the left side. So working our way up, we are approaching a y value of 6. As x approaches 4 from the right side, so we're working the other way, we're approaching the same point, positive 6. And again, because these limits match up, then we would say that the limit as x approaches 4 from either side is equal to 6. Again, another little fun fact with that, though, if I were to ask you for the value of of f of 4, that would be undefined. There is no point or value of the function at x equals 4. Even though the graph is getting close to it, that is a removed point or a removable discontinuity, so the function is actually undefined there. Now for the bottom two, limit as x approaches negative infinity. So that means as we continue going left forever, we are working down this graph, and it is implied that there are arrows on the ends of these. So that limit would be negative infinity. So again, even though there is no limit to these y values, even though the y values are not approaching a finite value, we can still provide additional information to describe this graph. And that's why we don't just write does not exist here. We say that it's approaching negative infinity. So infinities are important information for us to gather. Now, on the other side, as we go to the right forever, this graph is heading up forever, increasing without bound. So we are approaching positive infinity. Now, speaking of limits that do not exist, there are some circumstances where if you are asked to find a limit, you are supposed to respond with does not exist. So these are 3 cases of those. So for this first one, if I were to ask you the limit as x approaches 1 of f of x, from the left side, we have a one-sided limit of positive 1. From the right side, we have a right-sided limit of 2. And because those one-sided limits are different, this would be a case where we say the limit does not exist. So we refer to this as a break in the graph, or maybe a break discontinuity. So anytime that you see 2 completely disconnected pieces approaching different values on either side of a particular value of x, then the limit of that function at that particular value of x does not exist. Second case happens with vertical asymptotes. So in this case, as as x approaches 2, the limit of f of x would also be written as does not exist. Now we just said, well, the other ones were going to infinities. Well, the issue here is twofold. First off, yes, they are going to infinities. On the left side, we are approaching negative infinity, though, and on the right side, we are approaching positive infinity. So it's not possible for us to give that extra piece of graphical information and answer just positive or negative infinity. We can't give 2 answers. Because we are going to different things on either side of that value of x, again, we describe it as does not exist. So this is very common with vertical asymptotes. Now, if we had a graph like 1 over x squared, where we actually approach the same value on either side, technically the limit still doesn't exist, but we could at least give that piece of graphical information and describe that we are heading towards positive infinity on both sides. Then this last guy, this is, I believe, the graph of the function sine of 1 over x. You guys remember from pre-calculus and algebra 2 a little bit, trig functions are called cyclical or transcendental function, part of the transcendental function family. Because they are cyclical or periodic functions, they make those waves. They repeat their set of y values or their range over and over and over again. And in particular, this guy, when we have 1 over x as the argument for this sine function, what happens is, as you see here where it gets really dark, that's because the function is really compact and it's oscillating back and forth really, really, really quickly. So this is referred to as an oscillating function, but in particular, it's oscillating so fast that even if you move the value of x a microscopic amount, it makes the y values jump back and forth between -1 and +1 very, very quickly. So because it's moving so quickly or changing so quickly, we can't ever really nail down the value of x, or excuse me, the value of y that we are approaching around x equals 0. So in this case, the limit in question is as x equals 0. Because it's oscillating so fast, we just don't have the ability to describe what we are approaching. So this is a third option. It doesn't happen as often. It really only happens when we manipulate some trig functions to make it do some weird stuff. But this is a third possibility for how a limit cannot exist. So now I have a new graph, new set of problems for you guys to practice. I recommend, it's your choice, but I recommend that you pause the video when I'm done talking here. Try these problems on your own, and then when you're ready, start it up again and check with what I go through to see how you guys did. So if you want to do that, go ahead and pause right now and then check back in. All right. So whether you tried them or if you are still struggling and you just want to follow along with me, let's go through these. So the first one, again, just getting used to the notation and being able to read it and know what it's looking for is really important here. So all three of these first ones are concerned with x equals 0. First two are directional. The second, or the last one, is overall limit. So the limit as x approaches 0 from the left side. I do recommend drawing little arrows on these graphs. It definitely helps visualize it. In this case, we are approaching a value of 3. And right off the bat, as soon as I see all these are concerned with x equals 0, I notice this break discontinuity. Because the graph is broken at x equals 0, I know that this limit is not going to exist, even without technically evaluating these two. It's never possible for us to have a limit if I have to jump from one point to another to continue the graph. So for the second one, though, the limit as x approaches 0 from the right side, we are approaching positive 1 there. And again, different one-sided limits means the limit does not exist. Next set, we're looking at x equals 2. So as soon as I see this, I see we've got a vertical asymptote. So just be aware of that. But as we approach 2 from the left side, we are moving up forever or increasing without bound. So we are going to positive infinity. From the right side, we are also going to positive infinity. So technically, again, the function is not defined at x equals 2. So technically, we're not approaching a finite value. So there really is no limit here, but there is additional meaningful information to write down and describe what this graph is doing. So it is helpful to us to say, as you get closer to 2 from either side, your y values will increase without bound. So that's what we're going to go with. All right, next point is x equals 3. So looking at this guy, I noticed that there is a hole there. Remember, holes in the past may have been an issue, or it may still be a little confusing to you, but as far as limits are concerned, a hole that the graph is connected to on either side is not that big of a deal. It's not something that's going to mess us up, because as I approach 3 from the left side, I'm working towards this point with a y coordinate of -1. Same is true from the right side, so the limit is still -1. So because I'm approaching the same thing from both sides, even though the function is not defined there, so even if I asked you to find the value of f of 3, I would have to say undefined because there is no defined point there. That does not affect the overall limit. So limit as x approaches 3 of f of x is still -1. All right, and now for the last two, we've got some limits at infinity. So as x approaches negative infinity, remember that is describing the left side of the graph or the left end behavior. We see that the graph is flattening out here. So as we go to the left, or as x approaches negative infinity, the graph is actually flattening out around the x-axis. So we know that this is actually a horizontal asymptote at a y value of 0. So that is describing the limit. So as we keep going to the left, the y's are going to come down and get closer and closer to y equals 0. On the other side, as we go, as x approaches positive infinity, or we go to the right forever, actually defined it for us here, and you actually see this. So sometimes you'll see these asymptotes drawn the entire way across the graph just because it's easier for computer programs to graph them that way. But really, this portion of it means nothing to us. The graph is not doing anything to that line on this side. It's really only important out here on the right side. As x approaches positive infinity, we see the graph is getting lower and lower, closer to that line. So that right side limit at infinity would be -3. All right, now let's just get a little bit more practice writing limits. So we're going to kind of do it the a little differently for this one. So I've got another graph here. We'll call this the graph of f of x. And we're just going to kind of go through and basically try to write down all of the limits information that we can possibly discern from the graph. So I'm going to kind of work my way left across the graph just to keep a little bit of an order. So if I start with the left arrow, it does kind of look like this may be peeling off and heading toward a horizontal asymptote, but we don't know that for sure. If they had extended the graph a little bit, we may be able to tell that. But so for right now, it just looks like the graph's going down forever. So we're going to assume that that's true. And in this case, we're going to say as the x approaches negative infinity, the limit of f of x will be negative infinity to describe that end behavior. Next value of x that would be of importance would be -4. If you look from left and right, it looks like they're doing two different things, so we're going to write them separately. So first, as we approach -4 from the left side, we are moving up forever, so that would be positive infinity. So that's describing the vertical asymptote there. But then as x approaches -4 from the right side of that graph, we are actually working down to that hole at -2. So, and that is possible sometimes. Again, when we work with piecewise functions, there's all kinds of crazy stuff that we can possibly describe. So because we looked at the limits from both sides of that guy, if we were to look at the limit overall of -4 without directions, then because we're doing different things on either side, we'd have to say that limit does not exist. All right, our next value would be at -2. And this time, I don't necessarily need to separate it. You could look at either side, but just looking at the graph, we can easily tell that from the left and the right, we are approaching a y value of 1. So because of that, we can just simply state that limit. We don't need the directional one-sided limits for this one. So limit as x approaches -2 is +1. At x equals +1, we see a break in the graph, so that one we will want to look at either side. So as we approach 1 from the left, we are heading down towards -3. So that's the left-sided limit. And then as we approach 1 from the positive side, the right-sided limit, we are approaching +1. So again, because the one-sided limits are not equal to one another, then the overall limit of f of x as x approaches 1, we say does not exist. And then the last value of x of importance would be this endpoint at 5. So because this function isn't defined beyond x equals 5, it's not possible for us to actually answer the question, what is the limit as x approaches 5? We don't really know what that is, or in this case, if there is more graph, they didn't tell it to us. But because it's a fixed endpoint there, typically that means that that is the end of the domain, that's the end of the graph. So this limit really, there's no need to ask that question. So all we can really answer is the limit as x approaches 5 from the left side, because that is the only side or the only direction that we can approach that endpoint and be on the curve. So in this case, that is approaching, let's say, 3. It may be just a little bit below that, but we'll just eyeball it. So for that graph, that is really all of the information that we can state using our limits. So now one last practice problem here with the graph. Now I've given you a whole bunch of limits information, and we're going to kind of piece all of this together to help us come up with a sketch of a graph. It may not be perfect. Again, there's a lot of things that you don't know just based off limit information. So we're just going to keep it very simple and put together what we do know for sure to be true. So the first piece, f of 2 is undefined. So we don't necessarily know anything just from that, but if I couple that with this statement that the limit as x approaches 2 of f of x equals 3, so if the limit exists but the function's undefined there, these two guys combined tell us that there is a hole at the coordinates 2, 3. So I'm going to go ahead and plot that. 2, 3, I know that there is a hole. I know because the limit exists that from the left and from the right, we are approaching 3. How we're getting there, we don't necessarily know that just yet, okay? Next piece, so the limit as x approaches -1 from the left is -3, and the limit as x approaches -1 from the right is 1. So because these are two different one-sided limits, from the left side, I'm going down to -3, and from the right side, I'm going up to +1. So what we don't know for sure is whether both of these are holes, if one of them is a defined point and one of them is a hole. That part we don't necessarily know to be true. So again, we're not coming up with the only graph that's a solution to this. We're just going to make a guess. So it really doesn't matter which one we pick. But what we do know for sure, there are coordinates on this graph at -1, -3. So I'm just going to plot a hole for that one. And then also, whoops, yeah, at -1, +1. So I'm going to make this one a fixed point. Okay. And before we draw any curves and stuff, we're going to look at the rest of this. Then at x equals 4, so as we approach 4 from the left side, we are approaching positive infinity. And as x approaches 4 from the right side, we're also approaching positive infinity. Again, the only way that we can approach a finite x value and have unbounded values is if we are approaching a vertical asymptote. And because these are the same kind of infinity, this is like a 1 over x squared situation where both sides are approaching the same thing. So I'm going to draw my vertical asymptote in here. And now I know for sure that as we get close to this line on both sides, we are moving up forever. Okay. And one last piece, the limit as x approaches positive infinity. So as I keep going to the right, f of x equals 0. So this is describing a horizontal asymptote only on the right side. So on this side of the asymptote, I know up here we are approaching positive infinity. And I know as I continue down this way, we are approaching 0. So that side I know is going to be fairly accurate, something like that. On this side, just again with the information that we have, we know after this point we are increasing without bound. Again, we could have possibly gone down and then come back up, but we're going to keep it simple for this. But we know we have to approach infinity because of that asymptote. So between these 2 points, again, we could go up and down and make all kinds of crazy turns. We're just going to keep it fairly simple. We know that as we approach -1 from the right side, we are getting closer to +1. And then on this side, as we approach -1 from the left side, we're getting closer to -3. But again, everything else over here, they don't give us any information for, so it could literally be anything as long as it's still a function. So again, based off the information that we know that there's a break discontinuity at -1. We're not sure which one's a hole or a fixed point, if any. We know that there is a removable discontinuity or a connected hole at x equals 2. And then we know there's a vertical asymptote at x equals 4 and a horizontal asymptote on the right side of the graph at y equals 0. All right, now we're going to talk about how we can evaluate limits using tables. So a lot of times you're going to be given a table of values. Every once in a while you may be asked to use the calculator feature, table feature to evaluate limits. So I'm going to walk you through both just so you guys know how to do it both ways. But the table process is fairly straightforward. It's really just a matter of looking at as x gets closer to my value on both sides, what are the y values doing? And that's really all there is to it. It's not an overly complicated process. The biggest thing to remember, though, is we have to approach both sides of our x value to make sure that we're approaching the same thing. So the first one we're going to try is this rational function. So the limit as x approaches 1 of the function x cubed minus 1 over x minus 1. So this is the first time through this section that we've actually seen an expression for the function rather than just the function notation. So just so you guys are aware, when we write these limit expressions, these are very similar to trig functions where they have an argument. So I want you to think of it as kind of like the box where the function is inputted into, and the limit operator, this stuff, is attached to that box or that argument. So just writing this notation on its own means absolutely nothing. It has to be attached to a function to tell you what to take the limit of and where to plug those values of x into. So that is what this argument box of that expression is used for. So we can put function notation in here, so we could use the name of the function, or we can actually give the expression that the function is equal to. So in this case, we're working with x cubed minus 1 over x minus 1. So there is some algebraic techniques that we can do with this, but I first want to show you how to do it in the calculator. So if you don't remember, it may have been a while, when we go to graph functions, or if we want to use the table feature to input values, we have to use the y equals menu. So top left corner. Um, this is a rational function, which means I need parentheses around the numerator and the denominator. So I'm going to do parentheses x cubed. So you can use the caret button to get cubed, or you can actually use, if I delete this, you can go to math, and then the third option is actually the cubed power, so you can do it that way as well. So we got x cubed minus 1, close parentheses, and then divided by, and then open parentheses, x minus 1, close parentheses. So again, anytime you're typing a rational function into y1, make sure that you have numerator with parentheses and then denominator with parentheses. So you could graph this function if you want. We can do zoom 6 to make sure the window looks nice. So you could make the graph. Now, if you look at that, that actually looks like a quadratic function, and it is. The issue is at x equals 1, the function is undefined. So if I were to use the trace feature and go to x equals 1 on this graph, you can see that there is no y value. So that's because when I plug the value of x equals 1 into the function, I don't get a defined value. I get an error message or an indeterminate form. So that's why we're going to use the table feature. So to work with the table, we're going to change some settings first. So we're going to go to second, and then the window button goes to our table set. So there are two modes for your table. The table can generate pre-made values of x for you if that's how you want it to do it. If that were the case, then you would make the independent variable set to auto, and it will automatically generate a value of x, or a set of x values, and that's what these numbers are for. You can tell it where to start and then how much to count by. So if you want to count by ones, you would make that delta table value 1. What I prefer is the ask method. This makes the table blank when you go into it, and then you can input whatever values of x you would like to have, which is helpful for us because we're not always going to count by the same amount. We want to scoot the value of x closer and closer to our value of x that we're concerned with. So once those settings are good, make sure your calculator is set up the same way. Then we're going to go to second graph to take us to the table. And you can see it's empty. So now let's go back to our notes. So the limit we're concerned with, again, is at x equals 1. So that means in my calculator, I'm going to start on the left side of 1. It can be anything, any value of x to the left of 1. So for example, 0 is to the left of 1. I can plug that in. But now I need to keep scooting that value of x closer and closer to 1 from the left side. So again, if you think about a number line, 1 is the value I'm concerned with. So I started with 0. So we basically just want to keep scooting closer and closer and closer until we see some kind of pattern going on. If the limit really does exist, you're going to see those y values are getting closer to a particular value. So let's say I wanted to do 0.5 and then 0.9. But right now, there doesn't seem to be much of a pattern. 1.75, 2.71. There's not much clarity there. So let's just keep getting closer and closer. So basically, we're just going to keep adding nines after that. So 0.999. Okay, now it starts to seem like there's a trend here. You can keep going. You're not going to see all those values. So it looks like I typed 0.99999, but the calculator wrote 1, and that's because the calculator can only fit so many digits on this table. So do be aware of that. It says 3 over here, but if you highlight it, it tells you the real value. Calculator, when it has too many digits to fit, it will automatically round. And in this case, that 2.99997 rounded to 3. It does not mean that the coordinates that I have right here are 1, 3. It means that I'm really close to 1 and the y values are actually really close to 3. So that in turn is my one-sided limit. So we can tell now that as x gets closer to 1 from the left side, the y's are approaching 3. So now I go back to the x column and I just repeat this process from the other side. So now I'm going to start with numbers that are bigger than 1. So maybe something like 2, and then work my way down to 1. So hopefully, if this limit exists, we'll be getting the same kind of pattern just on the other side of 3. So let's start at 2. So way bigger than 3. 1.5, coming down a little bit. 1.1, okay, a little bit closer to 3. 1 point, let's say 0.5. Okay, and we're just going to keep scooting closer and closer to 1. But again, all these values are above 1, and you can already see that we are starting to get closer and closer to 3. In fact, again, rounded value, rounded down to 1, and then rounded down to 3. So you can see these trends pretty quickly, okay? Another thing to point out about the table, there are only so many spots on this table. So if you noticed, I was actually rewriting over this last cell in the table. So just be aware of that. If you're trying to write stuff down, write them down as you go so that you don't lose them and have to continue retyping. But so back to this problem, what we just figured out was this limit as x approaches 1 from both the left and the right side, we are in fact approaching a value of 3. So that's how we would do it if I give you the function and you have to do it in the calculator. But more often than not, rather than giving you the function and making you do it that way, because we have other methods when I actually have the equation, more often than not, when you have to do it with the table, you'll actually already be given a table. And in that case, it's even easier than doing it in the calculator. All we have to do is make sure that we are keeping in mind our C value. So your C value is the value of x that's kind of hidden in the center of this table. We are getting closer and closer to a value of x from either side. And so we are simply concerned with, as we do that, what are the y values approaching? So as I work my way towards 1 from the left side, it looks like these y values are getting closer and closer to something, 4.65, 4.665. So it looks like we're getting closer to something. And then from the right side, as we get closer to negative 1, the same thing is happening, 4.68, 4.667. So it looks like we are getting closer and closer to 4. Looks really bad, 667. Or if you guys know, that repeated decimal, 0.666667, is the decimal for 2/3. So this looks like we are approaching 4 and 2/3. Or actually, I'm going to make this just 6 repeated. So 4 and 2/3 is actually the same thing as 14/3. And that is the limit of this function. So I can write my limit notation, the limit as x approaches -1, and we're approaching the same thing from both sides. So I don't have to write one-sided limits unless it asks me to. Because the limit exists, I can just write it as the non-directional value is equal to 14/3. And that's it. That is all for evaluating limits graphically or using tables.